Alright, continuing this series of videos, looking at the lectures of Professor Lewin, MIT and all, and examining some of the theory. So in the previous video, it ended with some conversation about a Leyden jar, and I thought I would add a little bit of clarification to what I think is happening. So I'll attempt to do this quickly. Alright, so we have the two surfaces with 30,000 volts across them. Let's just say this one's plus and this one's minus. And then we have a insulator. Hello?
Hello.
Hello?
Hi, my name is Irene. I am calling on behalf of Big Brothers Big Sisters.
Jeez. Irene calling on behalf of. Anyway, yeah, sure. I trust you, Irene. I don't think I do. Anyway, it's annoying. I really don't want to start the video over. I probably should, but so what? We'll just do this and get it over with. All right. So there's the glass is essentially touching the other surface. Okay, so this is all glass in here. And the idea is why does the 30,000 volts end up sticking to the glass? Well, what's happening is because the glass is touching, and it's a conductor, so the two surfaces are very close to each other and touching in places. The conductor, will give its charge up because it's a conductor. It just is. So it's depositing its positive charge onto this glass surface. So the glass surface is going positive. So this is positive, and this is becoming positive. It's taking the positive charge off the conductor. Now, when this layer of glass goes positive, that's creating a magnetic effect, essentially. The gravity force comes straight down, blah, 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 blah. It goes through the filter. The filter says, I'll attract a negative charge. And so here you have the opposite surface down here. I don't know how to draw it, but so here's the opposite surface of the glass. So this is the glass surface here. And so this attraction process, the negative charge, so this one has negative on the conductor. So the conductor is here. It's negatively charged, and it's essentially attracting those negative charges, which is pushing them right onto the glass. You can kind of figure that out. And as it pushes negative charge onto the surface of this glass, that attracts, but it's only 3 millimeters distance here, that essentially says, I want more positive charge on here. And so this side says, I'll give you more positive, I'll give you more positive. And then this side, I'll give you more negative, I'll give you more negative. And so the conductor completely drains. All of its charge disappears, and all the charge ends up on the glass because the glass is closer, and the positive and the negatives are attracting each other. So that's why the glass accepts the charge. It's because it's not too thick. If it was too thick, it wouldn't happen. But if it's thin enough, it'll happen. So that's what's really happening. The glass is not conducting, but the glass is, in a sense, telling the one side of the glass, once it charges, it's basically telling the other side, take more charge. And then the other side, once it gets more charge on it, once the negative starts going higher, then the positive says I can take more charge. And then as that goes higher, like I said, it just induces the charge onto the surfaces. So all the charge ends up on the glass surface, not the conductor surface, because the glass surfaces are closer together. So the charge is just saying, I want to get as close as possible. Positive and negatives want to get as close as possible. The closest possible they can get is on the glass surface, not on the conductor surface. The conductors are far apart. The glass is closer together, so the glass surface is where all the charge goes. Yeah, I think it's pretty good. I think it's enough for the people who get any of this stuff. You should be able to get that. Anybody who's a physics student should have understood what I just said. Anyway, a student of physics. Let's say that. All right, on to the next lecture, which is, 15? So that should be right here. And
we've seen last time that using the Lewin formula, that if you have a current going straight into the blackboard, perpendicular to the blackboard, that we get a magnetic field at a distance r. The magnetic field tangentially to the circle, be here, and that.
Alright, so the B part again is the way the charges line up. Like I said, around in any circle, the charges will always end up pointing on these sides. They're heading in a direction, so to speak. They're not moving in a circle, but just because they're flat objects on top of a round thing, their pointy end sticks out like a sawtooth. So this becomes their magnetic field. So it's going to be north at one end, and the magnet's going to be leaving at the other end. So it's going to be south-north here, and north-south here. So it's going to end up with a south and a north pole facing any direction. So any way you look at the circle, you're going to end up with a north and south pole. And as you go left to right, you're going to have exactly the opposite orientation. So it essentially turns a circle into a polarized object. That's what the right-hand rule is basically a consequence of. That's what's a consequence of the rule. The fact that it always goes north-south, like north-south on the top, that's a rule like the spiral in a toilet. So that's a rule that has to do with some other mechanical feature in the world. And so it might have to do with how we're moving in a galaxy. It might have to do with some subtle thing, but I haven't defined what that is. Just as I'm not 100% sure why it goes left or right as a spiral.
Strength of that magnetic field equals mu 0 times I divided by 2 pi r. If you walk around this circle, just walk around, and you carve up this circle in little elements dl, and you calculate the closed circle integral over a closed circle of b.
So the interesting fact is like I said, the middle part doesn't have anything to do with the polarization. The part that matters is the part sloping towards you and the part sloping away from you, but the part that's deliberately facing you is irrelevant to the actual polarization.
Dot dl. So everywhere locally you dot b with dl, but b and dl are in exactly the same direction everywhere. Then you would find that this obviously is b times 2 pi r. But b times 2 pi r equals also mu 0 times I.
So, just such rubbish, these constants all over the place. So we have 2 pi r equals mu 0 times I. Mu 0 is a constant, the permeability of space. So, if they just weeded out these constants, you might be able to get somewhere with this nonsense. I mean, there's obviously a proportional relationship between the radius, r, and I, by that definition.
This dl here has nothing to do with this dl here. Don't confuse the two. This dl is a small amount of length in the wire that goes into the blackboard, which carries a current. This dl is simply u and dl when you walk around this current wire. And it doesn't matter at what distance you walk around, you always get mu 0 times I. You see it right in front of your eyes because b is inversely proportional to r. And it was Ampere who first recognized that.
Okay, yeah, you can't help but capture something if you have it surrounded. So obviously if you surround something with like a fence, then anything that happens, anybody throws a rock, it's going to hit the fence. None of the rocks can miss the fence.
You don't have to walk around in a circle to get the answer mu 0 I, but that you could walk around in any grouped path, as long as it is a closed path, something like this. And now you have here the local b, which of course is perpendicular to this radius, and here you have your local dl. And if now you go around, closed circle of any path, doesn't have to be a circle, dot dl, that now becomes mu 0 times I, which is known as Ampere's law, and I then is often given an index enclosed. It is the current which is enclosed by that path.
All right, so the B going up is just saying this thing enclosing is a round wire, essentially saying, and the round wire will have its polarization pointing up, which means the B up means there's a north going this way and a south going this way. It's still a dipole. The wire is polarized. So when it makes a B field, it's not really a B field. It's not just one thing. It's not just north. B field is magnetic, which means it's a dipole, so it has the other element, which is the south influence. So in a sense, it has arrows going in both directions, if you wanted to be accurate about it, or fair.
It's actually easy to prove this using Biot and Savai's formalism. This is almost the third Maxwell's equation. We already had 2 out of 4. This is almost number 3, not quite. We're going to amend it in the future.
What I'm saying is, if you made that enclosed surface fatter, you'd see that the field, the magnetic field, is going north this way and south this way. You'd see your right-hand rule visually. You'd see the clockwise motion pointed right out. It would illustrate the motion right to you. So if they drew these vectors by illustrating that the conductor has a polarization, if you're going around something, you say this is your flat surface, perpendicular to that flat surface is basically just saying this is the way we're looking at the conductor, and now if the conductor is going this way, towards me, this is the north end, this is the south end. You'd see it visually, north, south. If they just use 2 arrows for the magnetic field, it's a dipolar field, and yet they use a B vector thing and say, there, that's all we're going to do is draw 1 arrow for a dipolar field. It's not really a field, you know what I mean? A force.
What is ill-defined a little bit in this equation is what we mean by enclosed. And I'm going to define that now so uniquely that there is never any misunderstanding. If I have a very strange looking closed path that I have chosen, that's the path I walk, I have to attach to that closed loop a surface, an open surface. That's mandatory. You can make it flat, that's fine. You're free to choose it. You can also make it sort of a plastic bag, so it's open here. You can put your hands in here and here. It's like a hat. Any surface is fine, but you must attach to that loop a surface. So here I have some paths that you could be walking, and this would be a perfectly fine open surface. Could be flat, but it could also be open. So it's like a hat. And now I can define uniquely what is meant by this I enclosed. Because if now I have a current that goes through this surface and pokes out here, then I have a current penetrating a surface, and that is uniquely defined. And if I have another one coming in through the surface, call it I2, this is penetrating that surface. By convention, if you go clockwise around, we follow the same notation that we had before, the right-hand corkscrew notation, the connection between magnetic field and current. If you go around clockwise, seen from this side, so you go clockwise, then I1, as I have it here, in your equation would have to be larger than 0. I2 is then smaller than 0. But if you decide to go counterclockwise, which is perfectly fine, Ampere's law doesn't at all dictate in which direction you have to march around, then I1 would be negative, and then I2.
This is just talking about which way the current would be flowing, this way or that way through the wire, by going I more than 0 or less than 0. It's not very useful. Switching of the terminology doesn't help any.
Would be positive. So we follow the right-hand corkscrew notation. And so if you want to amend now Ampere's law to do me a favor, but you don't do books a favor, because all the books use the word enclosed, I would like to see this replaced by penetration. It is the penetration of a surface of a current. That is uniquely defined. But a current enclosed by a loop is ill-defined. Because where possible, but
The confusion this creates is that you have more conductor going through the surface than if you're using a bag. Then you have to consider more of the conductor, more stuff you're trapping inside the bag. There's more conductor, there's more wire inside the bag, and that makes it a hell of a lot more complicated, I would think, because you have to figure out how much wire is inside the bag.
when we apply Ampere's law, we will try to find easy passes around circles sometimes rectangles. And since you're free to choose the surface that you attach to the loop, if you can get away with it, you use a flat surface. But you cannot always get away with a flat surface. So the recipe is as follows. You choose your closed loop. Any loop is allowed. It may not help you very much if you choose the wrong loop. Any loop is allowed. You then attach an open surface to that loop. And I penetrate is now the current that penetrates through that surface according to this convention. And the direction of rotation is free to you. How you go around the path, it's your choice. But that defines then the sign of the penetrating of the curve, of the current according to the right-hand corkscrew. So now we can, for the first time, calculate the magnetic field inside a wire that draws a current using Ampere's law.
Alright, so there's no field inside the wire, blah blah blah, all this stuff. The wire is turning into a filter. It's creating a field. It's not, it doesn't have a field.
I have here a wire that has a radius capital R, and a current is coming to me, I, and let's assume that the current is uniformly throughout the wire. So it has a uniform current density. And I would like to know what the magnetic field is everywhere. The cylindrical symmetry, I want to know outside the wire, and I want to know inside the wire. Let's first look.
So again, inside the wire is just playing a game, because it's not happening inside the wire. The wire is turning into a bunch of little magnets when the current's on. This is another subject I wanted to talk about, was the difference between charge and currents in wires. And it's sort of the difference between paramagnetic and ferromagnetic or something, or permanent magnets. Charge creates a magnetic field without anything having to move. No electrons have to move, all that kind of stuff. Nothing has to move. The charge doesn't have to go anywhere for it to be creating a magnetic field. A conductor is not magnetic until you're running current through it. That means it doesn't create the little magnets. So when something's charged on its surface, the little magnets are created by the charge. They're there. Okay, it's a monopole. Charged plus, charged minus. But it's a magnetic monopole, and it has real filtering capacity, where the conductor only has filtering capacity, that is, it's only magnetic, while the current is moving, while it's exchanging pressure and creating the imbalance in the configuration of the atoms and creating polar atoms, atoms that are negative and atoms that are positive, by imposing pressure.
At radius which is larger than R. And so here we have the cross-section of that wire, radius R. The current I is going through this surface. I now have to choose a closed path. Since we have cylindrical symmetry, it is clear that we would choose a circle with radius little r. So we can be sure that the magnetic field strength is the same everywhere because of reasons of symmetry.
And you might as well just change. You might as well just choose the first R, the capital R as R. You might as well just make your surface right on the surface. Save you a lot of trouble.
Since the current is coming towards me, and I'm free to choose in which direction I'm going to march, I know that the magnetic field is in this direction, so I might as well also march in this direction, so that my DLs are all in this direction. I don't have to do that, I could march the other way around, but if I march counterclockwise, then both terms left and right.
So again, he has it coming out of the blackboard, all right, which is fine, but again, there's a north side of the conductor and there's a south side of the conductor. So there really should be two arrows pointing out that you have polarization of that conductor. The conductor's been polarized by the first initial charge current that's creating a filter. That filter is causing the other wire to become a filter. Okay, and it's a polarized filter.
Of Ampere's law will be positive. I now have to attach a open surface to my path. Well, this will be, the blackboard will be that open surface. And so now I apply Ampere's law. So I get B times 2 pi little r, because dl and r and b are in the same direction, so it's a trivial integral. That now equals mu 0 times I, which now penetrates my surface, uniquely determined. All this current from this wire that comes to me penetrates my surface. So times I, and so B equals mu 0 times I divided by 2 pi r. And that's the same result that we found last time when we applied BO and so y. So there's no surprise that you see this. But now we have a way of finding the magnetic field also inside the wire. So here we have now the wire again.
So again, it just drops off by the r factor, and the 2 pi and the nu 0 are just constants that basically you could wipe out. So you just have the current falls by the r factor. It's just I over r essentially. I divided by the radius. So the more radius, the less you're going to have current.
The cross section, current coming out of the blackboard. And now I want
I'm saying the less magnetic field that's going to exist at that distance.
Which is smaller than capital R. And of course, my closed path, again for reasons of symmetry, is going to be a circle with radius r. And my surface that I attach is a flat surface. And so here I go, B.
So again, the whole point is this is one-dimensional. These are flat surfaces, pieces of some slices. And if it was a circle, you were talking about gravity or something, it'd be just r squared. So the field strength would be the amount of charge, the current in this case. The current's creating the charge, divided by r squared if it was round. So it's just, yeah, this could be stated much simpler than this.
Times 2 pi little r equals mu 0 times, now I have to be careful. Because now not the full current I is now penetrating my surface, but it is only a fraction that penetrates the surface. And the fraction that penetrates the surface is now little r squared divided by capital R squared times I. You see, because the total current comes through the radius capital R, but I only have now a circle with radius little r.
Right, so he's assuming there was a field inside the solid conductor, and that somehow you could test that, which you can't. This is just kind of let's just pretend the inside of the conductor is the same as the outside of the conductor, which doesn't make any sense at all to play this game. And then pretending that the conductor is somehow equally distributing the current, which we don't have any evidence that does that either. There's some evidence that pushes most of the work to the outside of the conductor. Most of the deformation of the atoms is going to be on the outside. The filtering capacity of the conductor is going to be more its surface than its interior.
And so I lose one r here, and so you get a very different result. You get now that the magnetic field equals mu 0 times I is now linear in little r divided by 2 pi capital R squared. And this grows linearly with r, whereas this falls off as 1 over r. And if you substitute in this equation r...
Now you're only doing that because of the difference in the area of the circle, the circumference. As you make the circumference bigger, you square the circumference. You make a little change in the distance, the r, and that creates a big change in the circumference. So little change in the r, big change in circumference. That's why there's an r squared.
Equals capital R, which then would be the magnetic field right at the surface of the wire. You find exactly the same result here. Little r becomes a capital R. If little r becomes a capital R, you lose one capital R, you get the same result. And so if you make a plot of the magnetic field as a function of little r, then it looks like so. So this is little r, this is capital R, And this is the magnetic field strength, but we know that it is tangentially to these circles. It would be straight line, and then here it falls off as 1 over r. And the maximum value here is the value that you find there if you substitute little r equals capital R.
Now he's just talking about you go from the center and going out. Obviously it's getting more and more charge as you add more and more density to the amount of conductor involved. That's you're allowing to be part of the equation, and to get that peak value on the surface, that's the top, the peak, and then as you go further distance it lowers.
I will now show you that we can, using Ampere's law, also come very close to calculating the magnetic field inside what we call solenoids. Solenoids is like a slinky current that goes around in a spiral, one loop after another.
Yeah, I thought we already did that earlier, but comparing a solenoid to a conductor, in my opinion, is just breaking every rule possible. I mean, they don't have anything in common, so it's just wrong. I mean, the solenoid is a wire with an empty space in between. It's not a solid conductor. Not exactly comparable.
I want to remind you that if we had a loop, a nice current loop coming out of the blackboard here, and the current going into the blackboard, so there's a circular wire, but I only show you the cross section. I want to remind you that the magnetic field, as we discussed last time, would be clockwise here, would be counterclockwise here. In the middle, remember, it was like this.
And remember, so when he draws these numbers, he really should show the two conductors with the arrows in the right places, which is going down and going up, and the other one has an arrow going down and going up, right? To be because these are the ones that are going to repel the opposites. The opposites repel in this circumstance. So the one coming down is going to be meeting one that's also going down. They're going to have the same polarization facing each other. They're going to be like magnets. So it would have been better to point out that see, just where he has the arrow going counterclockwise, that means the arrow is going down on the left side and up on the right side. And when he has it going clockwise on the other one, that means it's going down on the right side and going up on the left side, which are opposites, so they should attract. I'll get back to that. Oh, well, they're opposites. I forgot you have to reverse them. One's upside down. So if I put them on a flat surface, it's the way I'm looking at it, it's wrong. I'm just saying it'd be better, instead of having the arrows going this way and this way, the arrows should be in the direction of the thing that's looking at them. So they should be showing what side is north and which side is south, rather than just saying what direction it's going in. Because the direction is essentially telling you what side is north and which side is south. That's the way to say it.
And then in between, it was like so. That was sort of the magnetic field configuration in the vicinity of a loop through which we have a current going.
Repulsive. That's the shape of repulsive fields. So the two magnets are the same orientation.
But now imagine that you put another loop here, current again coming out of the blackboard going into the blackboard, and another one, and so on, several. What do you think is going to happen with these magnetic field lines which now diverge? They're going to be sucked in here. This loop also wants the field lines to come through its circle, so to speak, and this one too. And so you're beginning to get a near constant magnetic field. And the more tightly these loops are wound.
It's like any pressure argument. The more things you poke something with, like I could poke something with 2 points at a far distance, and there's going to be room for stuff to bulge out and to be disfigured. And the closer I put them, though, the less they can bulge out, so the straighter it becomes. So you're just eliminating by having many loops tightly looped. You're eliminating any gaps that would allow deformation.
The more accurately will your magnetic field be approximately constant. And I have some transparencies which will show that in more detail.
So you use the word sucked in, which I think is just another term that was just wrong to use. That process has to do with which way the current's moving. Essentially, when you're coiling wire, you're essentially coiling it in a direction. And the magnets are moving, theoretically. Okay, the head and tail of the magnet, whatever you want to call it, the magnet itself isn't moving. The atoms aren't moving, but the atoms are switching from plus minus to minus plus constantly, and they do that just by having that extra pressure from the electron. So the extra pressure, when they're pressurized, they're turning into a north pole. When they're depressurized, they're turning into a south pole. So they just keep going from north pole to south pole, north pole, south pole, north pole, south pole. And by doing that, they're essentially magnets on the move. And so anything you put in that field is going to be sort of dragged by that movement. That's what's pulling. There's no current around the magnets. The magnets have to literally be moving. The magnetism essentially literally is moving in a direction, and whatever you put in there that's paramagnetic is going to acquire that same tendency to move in the direction that the magnets are moving. The magnets are essentially going to pull it, but the magnets are going to pull it, not the current.
Here we have a figure. You see 5 windings, spiral. If you look from the left, the current is going in clockwise direction, and so the magnetic field is going from this side to that direction. And when you look here, you see that the magnetic field is approximately constant inside, and outside these.
So again, it's just this idea that somehow there's a magnetic field's lines are somehow active lines that are active. The lines aren't active. The magnets are active. I know. I keep saying it over and over, but I mean, it's really a big mistake in their perception.
Current loops outside the solenoid, we call them solenoids, the magnetic field is extremely low. And if you start winding these.
So I've explained why it's extremely low. It'd be extremely low on the inside too. If he did just 5 windings, it would be extremely low inside there, because there's lots of places for the energy to escape, lots of gaps. You have to eliminate the gaps, and then you create a multiplier. You create an internal surface where the force can't escape and just keeps reflecting and keeps magnifying the force. So the force gets magnified on the inside. The outside force is actually the real amount of force. The real amount is really tiny, and it only looks big when you coil the wires and trap the force inside. So you're trapping a bunch of this electron force inside the coil.
Loops very tightly, then you get a configuration looks like this. You get an almost perfect constant magnetic field inside the solenoid, and the magnetic field outside the solenoid is extremely weak. And now I would like to.
So this is pointing out again, the field that the wire, a conductor, creates is weak. If I take a straight wire and make it go long distances and stuff, you won't. The magnetic field is nothing, because it's just tiny. And it's only by this gimmick of rolling that field on top of itself and creating a trap where it can't get out. And it's like a mirror inside. And so you just think of it mirror inside with photons, and the photons can't get out. And they just keep bouncing back and forth. And every time they bounce back and forth, they're creating the magnetic effect. So every transfer equals more magnetism, essentially. So every impact of that force. On the outside, the force just has one impact, and that's it. It's done. It can't do anything more. On the inside, it keeps multiplying.
Calculate with you using Ampere's law what that magnetic field inside such a solenoid would be. And we have to make a few assumptions. Let this be my solenoid. And the length of the solenoid is capital L. The current I is going through like so. I. And I assume that if I look from the left side that the windings are wound clockwise, so I know that the magnetic field is then in this direction.
So again, just kind of obvious. It's a like I said, if you thought of it as magnets moving with the current, you could sort of understand that if the magnets are going that way, they're going to push whatever other magnet. If I shove a magnet in there, the magnet's going to go that way. It'll be pulled along.
I make the assumption that the magnetic field outside the solenoid is approximately zero. I will show you later with a demonstration that that's a pretty good approximation.
Well, like I said, it's really not. So, but you know, I'm just saying compared to the field inside, it looks like zero. But again, it's just because the coil is magnifying the effect by trapping the force. The magnetism hits the conductor and hits it and hits it and hits it.
And so the question now is, what is the magnetic field there? And I assume I have n loops, n windings, capital N. So now I have to choose a path. I have to apply Ampere's law. I choose a path. And you may be surprised the path I'm going to take. This is the path I choose. It's a rectangle. And the length of this side inside the solenoid is L. And I think of this as 4 different passes. Number 1, number 2, number 3, and number 4.
Right, and 1, 2, and 3 are all going to be irrelevant because he's already declared, he's already pointed out, I'm going to call whatever's on the outside 0 because he's going to just pretend it's 0. That was one of his assumptions. And obviously the two going this way and that way can't possibly collect any of the energy because the energy's radiating this way, and that's like having it's like having a solar panel pointed at the sun, you know, flat. You know, the sun can't hit it. It has to be pointed this way. The sun has to hit it. So those two lines can't catch any field energy because the field energy is leaving as rays. So they can't get hit by much. I mean, they are getting hit by some, so he's just saying it's going to be 0 probably, but it's some, but it's not enough to worry about.
Let's first look at number 2. We have assumed that the magnetic field is practically 0. So clearly, if you go the integral, if you go around, then the contribution here must be 0. If the magnetic field is 0, then the integral B dot dl is 0. So that's easy. But if you look at 1 and 3, there is no magnetic field, very small magnetic field outside. The magnetic field inside is in this direction. But the L is like this if I march like that, and B is like this, so they have 90-degree angles, and so the dot product is 0. And so the only path that contributes to my closed loop integral of Ampere's law is only path 4, and that tells me then that B times little l, because B is constant, I have assumed that it is constant, and I integrate it over a length little l. Now I have to agree on my...
See, the flat lines are getting hit by some in the sense that, obviously, as I pointed out, the magnets aren't moving. There's nothing moving this way, so it's not going to hit this surface this way. The force is moving back and forth inside that coil. But the truth is, some of it's moving at angles, so some of it's going to perforate that surface. But the truth is also that for every bit of N energy it's hitting, it's probably going to get hit by as much south energy, and so it might end up being a net 0 anyway.
Surface. What surface am I going to choose to attach to that closed loop? Well, why not using a flat surface, just like the blackboard? So now I have to calculate the current that penetrates that surface. The current that penetrates that surface, I have to know how many times this winding pokes through that surface. If the length of my rectangle is little l, and if the length of the solenoid is capital L, and if there are n windings on capital L, this is the number of times that the current pokes through that surface. Uniquely defined. I have a surface now. There is no such thing as I enclosed. That is, I penetrate through that surface. It's a soap film, and I poke straight through it, and I do it so many times that I...
Right, and it really matters how thick these conductors, this wire is to some extent, because obviously that's a limiting factor in deciding whether you've closed all the empty space. So in theory, the real point is, have you closed all the gaps between the wire? If you haven't closed all the gaps between the gaps between the wire is where the force escapes, and that's where you lose your energy. So this equation only works if the assumption is these wires are going to end up being right next to each other, because they're the right thickness for that to happen. So that's another assumption built into this equation, is that these wires aren't creating any air gaps, any gaps between the coils. As you wrap them, they're right next to each other. If they're gapped, this equation won't work.
Poke through it. And then I have to multiply this by mu zero, and then I have my I. Each time that it pokes through, I have current I. And so what you see now is that B equals mu zero times I times N divided by L. And so that is our prediction for approximately constant magnetic field inside a solenoid.
With the assumption, that's not stated by him, okay, that your conductor is of sufficient thickness that N windings will equal L. So you will have, the windings will fill the entire space. That's the assumption. So there should be another variable in there that says, N times the thickness of the wire equals the L.
And this actually is a very good approximation as long as L, the length of the solenoid, is substantially larger than the radius of the solenoid. The radius would be the radius of these loops.
Longer than the radius of the loops. Well, that point becomes moot if these loops can loop on top of each other. So if you can loop out this way, just keep looping on top of the loops, then that rule also disappears. So again, it's not a real rule. They're just talking about if you have loops that are continuous that don't overlap on top of each other, then it matters that it has to be longer than it is fat. But it doesn't have to be if your wires are coiled on top of each other. It'll work even better.
I'll work out a numerical example, which is aimed at a demonstration that comes shortly. We have here a solenoid whereby N is about 2800 and L is about 60 centimeters, that is 0.6 meters. And I'm going to run through there a current which I really don't know yet, but it's going to be close to 4.5 amperes. We will see when we do the demonstration. And so I can calculate now what the magnetic field is going to be. So the magnetic field strength is going to be 4 pi.
So just understand that the wires have a sufficient thickness that those 28 windings going that, whatever it would be, 60 centimeters, 0.6, 60 centimeters, right? 100 centimeters in a meter. So anyway, should work out that way, right? So anyway, that the wires of sufficient thickness that the wires are right next to each other. That's built into this as an assumption. Because if it's not true, this equation won't work.
Times 10 to the minus 7, because that's what mu zero is. And then I have to multiply it by 2800. I have to multiply it divided by 0.6. And then I multiply it by the current, 4.5. And when I do that, I find about 0.026 Tesla. 0.026 Tesla, that is about 260 Gauss. And when we do the experiment, the current will be a little different. But you will see that indeed the field will be very close to 260 Gauss.
Right, and 4 Gauss is 4 ounces of pressure. So 4 into 260 would be 60 somethings, 65. So 65 ounces. So it'd be like 4 pounds of pressure. Something like that.
Why is it that the magnetic field is not proportional to the number of loops, but proportional to the number of loops per unit length? You may say, well, if I have one loop, I have a certain magnetic field. 2 loops, I have twice that magnetic field. 10 loops, I have 10 times that magnetic field. Well, imagine that we start a solenoid in lobby 7. And so here's lobby 7, and here is that solenoid. There it goes. All the way.
Right. Then your closed loop would have to go all the way from lobby 7 to be able to collect whatever effect you're creating, and obviously over the resistance of anything you try to collect it over, you're probably going to lose everything that you got.
Thousands and thousands and thousands and thousands of loops.
Very little reflection is going to happen with that much empty space.
We end up here in 26,100. Look at this loop. Think of it as the first loop. Creates a magnetic field. What is the shape of that magnetic field? Well, it is a current loop, and as we discussed last time, the magnetic field that one loop produces is like a dipole field. So do you really think that here in 26,100 we can sense the magnetic field that is produced by this one dinky toy loop? Practically nothing. It falls off so rapidly, the magnetic field, that we don't notice it here. So it's immediately obvious that the magnetic field is not proportional.
So he thinks that the magnetic field again is moving through the wire or through the distance, or there's some kind of, it's creating the effect along the length of the wire. So he's not even getting that what you really did is you got 2,800 windings, which means the windings aren't reflecting anything anymore. There's barely any reflection because the windings are so far apart that you can see that there's no opposite piece of wire across from anything. Nothing has an opposite on the other side anymore. So there's no mirrors, essentially. You've gotten rid of the mirrors and all the energy is just flying right past the other one, and you're not getting any internal reflection, meaning you have no magnification of the force. Think of the wire as a mirror. You stretch the mirrors out, that is, there's less and less mirror per length, then there's obviously going to be no reflections.
To how many loops you have. If, however, you put all those loops on top of each other, then of course you can add the magnetic field. And so it is natural that you get how many windings you have per unit.
So this is a real important, like I said, I'm claiming they got this completely wrong. They think there's a field inside the wire that's making something happen. And no, the field's coming out of the wire. The wire is interpreting gravity, essentially, and creating magnetism. And that magnetism is being reflected back and forth inside the wire because it keeps hitting a surface, the force, that's a mirror. And the mirrors keep reflecting the force, but the pressure created by each one of those impacts pressurizes the wire more, creating more magnetism.
Length. So now I want to first show you the magnetic field configuration of a very loosely wound loop with 7 windings, and I will do that by sprinkling magnetites, these iron file, in the vicinity. We've done this before for other current configurations. Now we'll do it for this solenoid with 7 windings, and I'm going to run a few hundred ampere.
So you're going to gain very little because look how much airspace you have. So there's going to be very little magnification. So you get some, but he's going to have to put a huge current through there to get any effect. Where you know that if you tightened up those wires, you could put a nail in there or something and create a very strong magnet. You know, with 4 volts or 3 volts of electricity, a tiny amount of current would create a lot of magnetism if you just tighten up those coils.
Through there, we first get this car battery, all right? And so we put some iron files on here, and what I want you to see now is that the magnetic field inside, even though it's very loosely wound, begins to look nicely uniform, and that there's almost no magnetic field outside. Look at this. Isn't that wonderful? Isn't that incredible?
But it's really weak, so they make a horrible solenoid because there's very little actual magnetic strength. Very weak. It's enough to move some iron filings, but it's not enough to move anything else.
You see how the iron files line themselves up very nicely, horizontally inside the loops, And when you look outside the loop, here or there, where we assumed the magnetic field was about 0, you don't see the iron file being oriented in any preferred direction, which indicates that the magnetic field is very low.
All right, probably a good place to stop. It's about halfway. Yeah, so I think we've done our job once again, and so I'll see you next time and such.